stream on YouTube and get started in 1 second. I'm just double checking if we're live on YouTube. Sometimes there's some issue that happens and I get paranoid about that. I can hear myself, which means I'm live on YouTube. Hey, everybody, welcome back. Thanks for joining us again today. As you can see, it's 3 people on the screen today, and we're super excited to host Jonathan. It's all thanks to Christian's help, who's also been joining us every week. Jonathan, thanks for joining us.
Yeah.
I'll quickly start by introducing today's session and introducing Jonathan, and then I'll hand it over to him. The topic for today is future of machine learning research in JAX and Flax. And this is the 3rd lecture, if I may, in our JAX study group. Last week, we learned about working with neural networks in JAX. This is being hosted with the JAX Global Meetup. If you're not part of the Meetup group, please go to meetup.com, search for this group. This is a group by Christian Garcia, who, if you're from the Flax community or the JAX community, would really trust him to learn about JAX, and make sure you're part of this group so that you can keep learning about JAX if you want to. So I'll quickly start by introducing Jonathan. Jonathan is a research software engineer at Google. He's one of the core developers on Flax. If you actually go to the Flax repository, he's one of the top contributors, actually the top contributor to the repository. He's done his master's in machine learning at Cambridge, and you can find him on Twitter at his first name and second name concatenated, Jonathan Heek. Jonathan, thanks again for your time, and thanks for joining us.
Thanks for having me.
I'll also introduce our co-host, Christian, who's been joining us every week. And you can also find him on Twitter at cgarcia88 to remind you all. He has been working on the 3X and LEG frameworks, which you should check out and we'll be talking about in our future meetups. And with that, I'll hand it over to Jonathan to talk about the future of ML research in Flax and JAX. As a reminder, I'll post the link to our forums in the chat. Please ask any questions there. Jonathan will be taking questions throughout, so please keep the questions coming.
Yes, please do. So thanks for having me. I'll give a little bit of an introduction. So I'm Jonathan. I actually, 3 years ago, when I started working at Google quite early, I figured out about this new exciting project called JAX, which was sort of this functional approach to doing numerical compute and using sort of the full power of the XLA compiler that was already there in the Tensorflow project. And it was sort of missing still a machine learning library to actually build neural nets. And then I thought, okay, yeah, let's try this out. That escalated and stuck to the wall, and so now we have this Flax project that is used quite a bit by researchers across Google and also in open source. Yeah, so nowadays we're actually thinking a bit like, where are we heading? We have this neural network abstraction, we can build the basic things, but sort of how is the ML stack? And in particular, the stack built on top of JAX, how is it going to evolve, and how is the research going to evolve, and what are the interactions that are going to be, and how can we enable sort of the tomorrow's research in JAX and Flax? Fundamentally, this is sort of a really difficult question, because if you would actually know what the research was going to do, then it wouldn't really be research. So I guess there's not really truly a roadmap, but we're sort of trying to plan for the unknown, so to say. This is also why I want this really to be a discussion, right? Because I want to hear from other people where they're going and what sort of exciting ideas they're going to try to throw on the wall, and what might stick, actually. But first, I want to sort of start with a bit of a helicopter view, a sort of oversimplification of ML research, if you wish. Right? We've got some basics now, right? Like a few years ago, you might still expect that sort of the CNN or this RNN that you're training today might be completely replaced with a completely different architecture tomorrow. Nowadays, we've got some things that actually stuck around, right? Like we've got normalization, we got like residual blocks, we got these basic MLPs, we've got attention. I guess sort of the exemplifying network here is like the transformer, which is really something that seems to be applied absolutely everywhere outside of the domain that it was actually designed for, which was like language. Now you're seeing it in like vision and translation and audio and pretty much anywhere. And it's sort of universally working well with minor tweaks. So this, I think, is actually a great thing, right? Like we've got some basic building blocks now in ML that actually work and that are actually pretty stable and that you can use everywhere, right? Like it's almost, well, it's not quite AGI yet, but it's pretty general, right? And it's relatively intelligent. Now that I think is really cool. And of course, in Flax, we want to sort of support that very well, right? And because you're using these basic building blocks all the time, sort of the friction to using them should be really minimal. And so that's where sort of Flax comes in. And the core of Flax is really the module abstraction that we provide, which we call Linen. And what it does is you already have JAX, but JAX is actually pretty fundamental because it offers you this NumPy API for building numerical computations and a bunch of functional transformations to do cool things with it, like taking gradients, compiling it, vectorization, parallelization, that sort of stuff. But if you're building big models, then there's actually some things that are not sort of natively supported in a functional paradigm, like things like variables and random number sequences. So parameter state, randomness. You need something to handle that sort of data flow and the flow of RNGs throughout your models. Otherwise, I mean, the great thing about functional programming is that it's very explicit, but there's a point where sort of a nice explicit API turns into something extremely verbose and repetitive, right? And so we want to make a bit of a balance there, right? Like we want something best of both worlds. So Linen modules provide that for you. So they handle the sort of the variable state, and at the end of the day, they provide it within an API that's that works with this functional paradigm, right? So at the end of the day, these stateful models offer you an init and an apply function that are actually functional, right? So unlike in perhaps a truly sort of imperative Pythonic API where the variables they sort of live forever as long as your program and the statefulness is unbound. In JAX, it's always like sort of confined within the smallest region, right? Like the smallest possible region, and we want to sort of at a global level still be explicit. That I think is really nice. Oh yeah, there's a question.
I have a question. Like the init and apply API, like was this taken from like somewhere specific, or did all the libraries suddenly rediscovered it? Like if you know the history of this.
So I think interestingly enough, there in Linen, there's not truly an init and apply. There's actually only apply, and init is a wrapper around it. What is the case though is that if you we support shape inference, right? So we sort of lazily initialize variables with an input example. So then naturally, sort of there are two stages, right? Like you want to sort of initialize the parameters of your models, and then you want to apply actual inputs to it to train it, right? So I think the init apply sort of distinction actually comes from the training loop, right? Like where sort of the initial part of your training loop is initialization, and then actually in the loop you apply the model, and then actually there might be an eval stage, right, which is like a variation of apply. So I think init apply is mostly something that comes from the training and not so much from the.
I see. Well, I was mostly curious because like. Actually, before Flax, I discovered Haiku, and then they also have init apply, and like my question is like, was it there like somewhere? Maybe Stacks, I think, also has it. Like, why why do all libraries converge to init apply? It's kind of my question.
Yeah, I think yeah, it's an interesting question. I think if you want to sort of stick a module into a functional training loop, that's eventually what you will have to provide, right? Like that's the sort of the language the common language that everyone speaks, right? I think this is also nice that this is so explicit in a functional language, right? That like, if you think that modules should at the top level be functional, then it sort of naturally converges to this tuple of functions, which in various frameworks might have slightly different signatures, but they're sort of like mappable to each other, right? Like there's sort of clear similarity there. I think this is actually one of the really nice things about functional programming, that very often people converge to the same thing because you need to make such explicit APIs, right? Unlike when it's imperative, it's much harder to make these sort of like, to see the similarities between these frameworks.
Okay, I'll ask you some related questions a bit after.
Sure. So let me pick this up again. So these Linen modules, so they sort of are embeddable inside the JAX framework. And apart from that, there's a few small extra utilities that we provide that we nowadays more and more branch out into other sort of independent libraries. But in the early days, we actually embedded them into the Flax repo. So these are things for like checkpointing and mixed position training and sort of small training utilities. And the other thing that we always, especially at the beginning, really like, because it was sort of lacking initially in JAX, is an example library which allows you both to sort of get started as sort of pedagogical like learning examples, but also forkable examples that really allow you to quickly bootstrap a new research project, right? So think about things like an ImageNet baseline, right? Like with like a ResNet 50 or like a transformer on a language task, which allow you sort of quickly take that thing, relatively clean, small code base, and try your research idea on it. So what these Linen modules look like actually is that you can have this, typically you'll have a call because you typically have like a single entry point to a module. So it behaves more or less like a function. And there's a setup which will always be called before it's used, where you can initialize submodules or parameters. And so sort of to stay within the sort of functional flavor, these modules behave like immutable data classes. So you provide some parameters on top as Python 3 field declarations, and those cannot actually be mutated after construction. And one of the nice things is that because init is lazy, you actually get automatic shape inference. So you don't have to track, like, for example, input feature shapes, right? So if you do like a reshape and then a fully connected layer, it will just figure out how many parameters that needs. And if you ever sort of call it with a different shaped input and the parameter doesn't match, it will like raise an error to you. And so at the end of the day, what that produces is this nested dictionary of variables. Now, when you get that back from Linen module after you did the call to init, it actually is just a nested dict of JAX arrays, right? So there's nothing magical about this variable abstraction where it keeps some kind of internal state or anything, right? Like at the end of the day, it's just a nested dictionary with some array data, which is, I think, one of the nice things, because this is sort of makes it very easy to manipulate it or to sort of feed it into other APIs or other libraries altogether, and let everyone just use this, right? Especially because JAX has this concept of pie trees where you can just map over an arbitrary container and manipulate it. And so one other sort of nice feature that I think is sort of in these simple examples, it shaves off a few lines, but I think actually if you make complicated examples, then what you get is that you have these really big module definitions where you sort of have to scroll up and down in your screen to sort of try to understand what this module is doing. And this has sort of a very large cognitive overhead where we have this API called nn.compact where you can actually define modules in line in this compact function. And it will just lazily create these modules for you and remember the parameters and the variables and the state. And this makes it sort of very easy because you can sort of, from the top to bottom, you can read the definition of this model and you know exactly what it does, right? And it does this sort of logical thing where, of course, you're not actually going to sort of recreate a convolution every time you call it, but you'll actually sort of reuse its parameters, right? And this is basically like a more declarative way of the, like if you would draw a network on the whiteboard in some kind of self-imagined pseudocode, this is probably a bit like how you would actually define a network, right? Like you wouldn't sort of split these things up because this makes it very easy to give a proper definition of the network that's easy for people to understand. And this is also actually how we want to actually have the real code be close to the intuitive pseudocode that you would use, right? And so that's why we provide this API. So then once you have actually a module, right? So you compose some modules together, some of the basic building blocks that Flax provides and some of your higher level modules that you created. Then you actually want to use this in your training loop. And we use this with these sort of these init apply functions. And when you init, you simply get a nested dictionary back with all the parameters and the state. And when you apply it, you provide those parameters and your inputs, right? And you get the outputs out. And if you want to have some state in your apply function, you sort of make that very explicit by providing this mutable field, and you tell Linen which specific type of variable is mutable. So in Flax, we have this concept of collections, where now the most obvious one is sort of the parameters collection, which has all the learnable parameters. And but you can have an arbitrary number of collections where you store your own stuff, right? So you might have a collection for like batch statistics for batch norm layers, or a cache for autoregressive decoding, or whatever you need. And you can sort of manage these things separately, right? So this allows you to say, well, actually, during evaluation, the batch statistics should not be mutable, but the cache should be. And this gives you sort of this extra little bit of safety. And it also sort of immediately tells you which variables might be updated and which updated variables you then need to handle in your training group, right? Because if you make a certain state mutable, it will also be returned by the apply function, and you will have to handle these updated this updated dict of state. So at the top level, it's a very explicit API that deals with whatever the sort of the modules internally create with their internal state. So I think that this approach has a number of advantages. I mean, first of all, there's just JAX, which I think is a very nice sort of clean API, which uses NumPy, which actually everyone who was to use Python already knows. These functional APIs, they tend to be a bit more explicit, and they lack this sort of like, if there is any state, it's usually very confined. So there's no sort of spooky action at a distance where you change some internal thing, and then the next time you call it, it behaves differently. And I always thinking like, you know, all these things I've tried in the past, all these research ideas that I tried in the past, like, were they just bad ideas, or did I actually just implement it wrong? And I have a feeling that a lot of people are actually thinking that, especially when you realize that a year later, someone else tries the exact same thing as you had in mind. And then suddenly for them, it did work. And then you really start to wonder, right? So actually, like the cost of bugs is really high in ML. And it's actually very difficult because I think in traditional software engineering, you can be pretty sure that if you have a bug, then probably the program or the compiler will just scream at you. But in ML, you will typically just get suboptimal results, right? And it's very hard to know what the suboptimal results are if you don't have a baseline implementation, which in research is always the case, right? So mistakes are incredibly costly and you might never find out that you made them, right? Now, some other advantages I think are, and this is mainly also related to XLA and how JAX interacts with them, is that you can run on CPUs and GPUs and TPUs, and you can compile for all of these platforms, which makes JAX pretty fast, pretty competitive with other frameworks. And you can also parallelize pretty well across devices. Recently, we've also had a change to how TPUs work. So this is on Google Cloud. So traditionally, how it worked is that you had a VM, and it was sort of connected over the network to a machine that actually had the TPUs, and it would send the program and the inputs over. And so this clearly has some limitations because you cannot actually run your own code, your own input pipelines on the TPU machine. And many programs, many ML workloads are actually kind of bottlenecked by the input pipeline, especially if that has to run on a completely different machine. Now, recently, there's this new approach where you can run directly on the TPU machine. TPUs are kind of nice because they come in very big scale and you can get a large sort of interconnected slice. And actually, JAX works really well with them. Compilation, XLA compilation is also very powerful for TPUs. So that this has been a very nice change where you can sort of run your own input pipelines and sort of feed it directly into the TPU. That I think is a nice bridge to sort of my second point on the helicopter view of the framework, which is that recently we've seen a huge success in taking these basic building blocks that we know work very well and are very stable and just scale them up massively. And this actually gives really impressive results. And this, of course, is perhaps not very academic, but it's sort of more of an engineering effort. Nonetheless, I think this is actually really powerful, and we should definitely not ignore this. Even if we don't have 1,000 GPUs handy, like perhaps OpenAI has. I think it's really crucial that JAX and Flax both offer sort of very good scaling opportunities. If you have an idea that works, you want to be able to scale it up, because in ML you can scale things up almost arbitrarily, and it will typically just get better and better. So the current parallelization strategy in JAX is that there's sort of two ways to parallelize something. One is Vmap, which allows you to automatically vectorize a program on a single device, right? So this basically adds a batch dimension to your program, which you don't have to manually take care of. Now that can be pretty nice, especially if you have sort of complicated, perhaps pre-written NumPy code that you want to vectorize. The other thing you can do is use Pmap, which is pretty much the exact same API, but it actually parallelizes across devices, right? So now there's sort of a map dimension, but it maps one-to-one to the devices that you have, and this can be on a single host or on multiple hosts. And this doesn't have to be a strict map, because of course, if you map over an axis, then strictly speaking, there's no communication across this axis. But in JAX, there are some special primitives that actually communicate along the sort of the map axis. So these have like little p names. So it's like a p sum or a p mean or a p permute, and they allow you to communicate over this axis, right? So for example, most neural networks are truly mappings over a batch dimension. But if you, for example, have a batch norm layer, then you're not really truly, you cannot truly map over your inputs, right? Because you actually have to sum over the batch dimension to calculate the batch statistics. And this you can actually do in JAX, even if you use Vmap or Pmap to sort of make this batch dimension implicit. But actually, this paradigm is being rethought a little bit. I think so far it has worked pretty well, but what we're realizing is that sort of these parallel workloads, they're getting more complicated. And so that's why there's now this experimental new tool, which you can already use, but it's still being built, which is called Xmap. And that sort of pulls apart the idea that some computations can be represented as maps and how you run them, right? So actually today already VMAP and PMAP have very similar sort of API signatures, which I guess is also what made people realize that perhaps these really shouldn't be two separate APIs. And so with Xmap, what you can do is you can Xmap a function and then map the input and output axes, the positional axes, to logical dimensions. So basically, you can give them a name that actually makes sense to what you're doing. Although here in this example, it's called like left and right, which I guess is not very semantically meaningful, but you get the picture. So you can change the positional axes to something which has a name. And so inside the function that you're mapping over, these positional axes will no longer appear. So if you want to sort of now use them, you actually have to use a primitive that can take in this name, right? So you might psum and give left, right? If you want to sum over the left dimension. Everything else is just implicitly mapped over. Then what you can also do is, oh, sorry, there's a question.
No, finish and I'll ask it at the end of the slide.
You can map these logical axes, right? So the semantically meaningful names to something that is meaningful to the hardware, right? So you can map these axes optionally to whatever sort of mesh of devices that you have, and you can map it to them, right? And this mesh specification is also separate from Xmap, right? So you define a mapping, and separately you define how that mapping is sort of mapped out to the devices that you have, right? And so there's a sort of hardware axes and there's logical axes, and you provide a mapping between them. And you of course put the devices on this mesh topology that you have, which typically represents the actual mesh topology that your devices have, right? So for example, on a GPU, you might have 8 GPUs that are closely connected, and then the rest sort of is connected over the net. And on a TPU machine, you have this 2D topology, right? Where all the TPUs are connected on a 2D way. There was a question, right?
Yeah, in this example, because, well, Xmap is kind of pretty new, right? Like, what is actually being computed here? And how does the mesh like treat the data?
So whatever mesh that you use, you will always actually compute the same thing, right? So it only impacts sort of the performance of how you compute it and not what you're actually computing, which I think is one of the nice things about this, right? Is that sort of parallelization here cannot break your code. I'll actually, I think, so this is a slightly sort of simple example. I'll have a slightly more informative example here. And I hope that sort of solves it, because here the logical dimensions actually mean something. So here's an example, which is perhaps a slightly over-engineered example, right? But just to keep things simple, where sort of all the axes are actually mapped, right? So here, basically, the only thing we're getting in is actually, it's all scalars, right? Like inside of the regression loss function. And then all the axes are actually mapped over, and we give them the names that like the logical names that they have, like batch and input features and output features. And here you can also see that the other thing that is changing is that there are other APIs in JAX that are very similar, very alike, is that of like numpy.sum and basically psum, right? Because they're actually both doing the same thing. The only difference is that in NumPy, you always provide a positional axis, and in psum, you provide a sort of a named axis that is mapped over somewhere else, right? Now, what is changing is that the NumPy API will still implement the NumPy API, But on top of that, it will also understand the named axes that Xmap provides, right? Similarly with things like einsum, right? Where you can now use a named axis rather than a positional. And so here you have an API which is basically everything is named, right? So now suddenly we got three things, right? We can basically write programs with named axes instead of positional axes. We can automatically vectorize things, and we can parallelize things, but they're all sort of decoupled, right? And modular. So we hit three birds with one stone, basically. That's what Xmap is doing. Do you still have a question about the?
Interesting. I think, well, for me, and I think a lot of the viewers, this is kind of something I guess you should play with, right? Because like initially it looks like, oh, you're putting names to things, but especially if you get to the mesh type of things, then it is not behaving only like a VMAP, but simultaneously like a VMAP, like a PMAP, if I understood it correctly.
Yeah, and so one other thing is that, so if you would here, for example, apply, so let's say we had just a 1D mesh, right? And we're just parallelizing over the batch. Then the other funny thing that happens here is that you can actually, so in PMAP, you actually had to one-to-one split, right? So you had to split over an axis that was just as big as the number of devices that you had. In Xmap, that's no longer the case, right? So let's say you had a batch size of like 128 and you have like 8 devices, then each will get a chunk of 60. And so how it will implement that is that it will do a VMAP and a PMAP over the batch dimension, right? So it will automatically vectorize over the 16 elements, right, that one device gets, and it will parallelize over the 8 devices, right? So here it will do a bit of both, so to say.
It's pretty interesting. I don't. Did you happen to see this post of doing kind of ocean, like an ocean simulation or something like that, a weather simulation? Came last week that was using like JAX for MPI, something like that.
I'm not sure if I've
I think Samjan featured it in the 27 days of JAX. Did you remember what it was, Samjan? It was ocean.
I'm trying to find the link. Yes, I'll just share it in 1 minute.
So now that you mention a mesh, like I remember like for the what he did in this case, maybe if Samjan can grab it, he split like a very huge domain into like subgrids, and then he computed something over the grid, and then he had to take care of the like boundaries between each grid.
Actually, I'll talk about basically that in a few slides.
Okay. Yeah, I was just thinking this mesh and I thought, oh wow, it seems like awfully similar to what he did there. I wonder like if it is something that could be like maybe because he used MPI, right? I am guessing he had multiple machines.
Jonathan, I've pasted the link in the Zoom chat.
So like I guess, I mean, JAX is still not very good for multi CPU. I don't know how we call it, like a cluster kind of thing. It's more suited for like a TPU cluster, right?
So GPU and TPU parallelism are a bit more mature, I would say, yeah.
Yeah, but if you have multiple GPUs, they have to be on the same machine, right? You can't have them on separate machines, or can you?
If I remember correctly, that has been implemented a while ago.
It has? Oh wow.
Yeah.
That works today.
Yeah, that should work today. Yeah.
Interesting. Then like I'm more curious why do you need OpenMPI? Well, I mean, obviously that's more for the developer of the post, but
Perhaps it might offer slightly more control, but I wouldn't be able to say for sure.
Okay, I see. But then what? Yeah, maybe you have kind of a similar example, but if you did get to see it, he created a mesh basically, and nowadays it is like, oh, it's kind of what you're talking about.
Yeah. Yeah, so people in our team and in Brain Amsterdam and others have actually built these big weather models that also operate on a very large input of weather data. This is the MapNet model. Like V1 was published a while ago, and then V2 was published recently.
I have a question. It might be a bit technical, but how would you deal with the border, like communicating between the boundaries? That was interesting in the article, but I wouldn't know how to implement it in what I know about PMAP.
Yeah, so in principle, you could do that explicitly, right? So, but I think the important thing is to sort of realize that if you have a convolutional model and you split up your input in parts, that's not really quite a mapping function, right? Now, of course, if you extend your mapping with sort of like, so in JAX, there's this p-permute function where sort of two indices of the mapped index can exchange an arbitrary value. Now, of course, you can manually slice up your border and exchange it with your neighbor. You can do this manually. It's very cumbersome though, right? Like it's sort of like it's very intrusive to your code, and you have to manually compute how that actually works, right? Because if you do a convolution, you have to sort of look at your kernel size, at your striding, perhaps dilation, and you sort of have to calculate exactly how much border you need to do this computation, right? It gets even worse if you have so much border interaction that the border actually extends across two neighbors, right?
Oh, wow.
This just gets terribly complicated. So it can be done as a map, but it doesn't look nice at all.
For PMAP, this would be, you would use the LAX API and communicate through there?
You would use lax.ppermute. That's how
ppermute, okay.
Yeah, that's how you do it. Oh yeah, and so here I wanted to just show so that all the things where you don't mention the axes, right? That you implicitly map over. What I wanted to go to is that my next slide is about actually an alternative approach where the example of where PMAP breaks down, which Christian has already introduced for me, is if you wanted to split up a large image and you wanted to run a CNN on it, then really this is very annoying, as we just described, because you have to exchange the borders, and doing this explicitly is very hard, and sort of it doesn't look very much like the thing you actually want to do. And so alternately to the Xmap development, there's another experimental parallelization strategy, which is called PJIT. Now, PJIT uses it's called JIT because it uses part of the compilation. It uses XLA compilation, but it uses an additional compiler pass. Now, what this compiler pass does is it takes a program and then it emits a new program that only works on a subset of the data. And what it does is it inserts communication primitives that make sure that the entire input is processed and the entire correct output is produced. So basically, it allows you to take a program and split it up automatically over multiple devices. Now, what it, for example, will do is if you give it a convolution and you split it up across its spatial dimensions, it will introduce these border exchanges, right? If you give it a data parallel program, it will introduce like a sum over the gradients automatically for you, right? So it will go through your code and it will just automatically add any parallelization primitives that you need to keep the code correct automatically for you, right? So this is completely implicit parallelization API. And the only sort of little help that you need to give it is sort of specify how the inputs and outputs of the whole function that you're compiling are parallelized, right? Like across the devices that you have. So if you did a very simple example, you would, for example, say like, okay, just partition over the data, right? And it might only add a single communication primitive to sum over the gradients and perhaps to sum over the batch statistics. But if you do something complicated, like splitting a huge image to simulate an ocean across spatial dimensions, then it will introduce all these border exchanges for you automatically.
Sorry, this was, you're talking about Pidgit?
Yes.
Okay. That is very interesting because it has very few documentation, right? So from the outside, you end up guessing what it does.
Yeah, so one of the I guess one thing that makes Pidgit a bit of an oddball is that it's not actually a JAX transformation, right? So it's not written in Python. It's actually part of the XLA compiler, right? And so the XLA compiler is not documented as part of JAX. We're like documenting what this thing does is actually an ongoing effort, but it's also a bit more difficult because it's not quite an explicit API. Right? It's a lot easier to explain what Xmap will do than what Pidgit will do, because Pidgit is really an optimization, right? Like it's actually trying to partition your program as cleverly as possible, right? So we're really talking about an optimization pass here, not a strict transformation, right? Like there are heuristics involved here, which make it more complicated.
But do you still help it with the mesh information and that kind of thing?
Yeah, so you do provide the mesh still. And you provide the sort of the how the logical axes, so how the positional and logical axes map to the mesh axes on the input and output side, and you can add arbitrary constraints inside the program. So you can so XLA will automatically sort of decide what is the most optimal sharding for each intermediate value automatically for you, but you can override this with a constraint, right? Where you say, okay, I specifically want this intermediate value inside this Pidgit function. I want that to be sharded in this way.
Can I ask kind of a devil's advocate question? It's kind of something that it's kind of a love-hate, I guess, in the end. For example, for me, if the compiler does something that I need for me is, I mean, it's beautiful. It feels like so natural. But then there's people who, well, like as criticism, they kind of say that you lose a little bit of control. I don't know if this is fair to state, because then you don't know what happens behind the scenes.
Yeah, so I think what's definitely true, right? Like if your objective is to make things as fast as possible, right? And you have a good idea of how the communication should actually happen to make it as fast as possible, you might want to use an explicit API like Xmap, because you know exactly what's going on. And if you want to check everything anyway, you might as well write it explicitly in your code. If you have an existing model and you want it to do a reasonably good effort, right? And more importantly, because that I think is really the main benefit of Pidgit, is that it guarantees you equivalence, right? Like you'll be able to parallelize your program and know that it will produce the exact same result as the unparallelized program, right? Which is with Xmap, of course, not the case. If you partition your code manually, you need to do it correctly. If you don't, it will make mistakes, right? Pidgit will not make mistakes. It might do something suboptimally, but it won't do it wrong, right? Which I think is sort of one of the main benefits.
Yeah, that is very interesting. I don't know if you have used or know a little bit about deep speed.
Yeah, so I think deep speed is an interesting. That's a pretty interesting library, and that's one of the things where sort of like comparing that is one of the things where we're definitely thinking about like how should the parallelization strategy evolve over time, because deep speed can do some things that are hard to do now in JAX. and vice versa, I think, right? Like, so this type of parallelism is hard to do in deep speed, I think.
From my perspective, like, I mean, PMAP is super easy to use. Like, I mean, you don't even have to know very much about distributed, like, systems or anything. It's just kind of like a VMAP, but you kind of have this notion that it's happening over multiple devices, but the details are taken care for you. That's the sensation I get. And then from deep speed, you have to take care of all the details, right? So it's kind of a trade-off there. Like in deep speed, you have to be more, send it here and then do this and then send it there.
Yeah, so what I think is cool is that JAX has been able to sort of, like, what's of course always in functional APIs is that you don't want them to just be functional, you want them to be really declarative, right? Like you want to declare what you're going to do and not sort of have this thing look like a to-do list of actions, right? Like an imperative API. I think this has succeeded very well and it's sort of like, it's becoming more declarative because arguably Xmap is even more declarative than PMAP was, right? And PJIT is maybe even more so declarative, right? Because you're sort of like declaring your function as if it's running on this magical VM that has all your compute resources bundled together, right? And now really partitioning becomes just a compiler, right? Just an optimization that happens, that's done for you. That I think is pretty nice. Of course, then deep speed maybe can also do some things that are kind of clever, like pipelining or streaming out in and out parameters that we cannot do today.
Jonathan, there's a question from the audience by Yuvraj, which is similar to this. So their question is, how can we have more insight on how XLA is choosing the most optimal path? Is there a way to comment on what XLA is doing in some cases, which might not be the case that one would want it to do?
Yeah, so actually, I think this is a bit of a problem that we have today and that we need to improve because profiling today could, in principle, you could try to reverse engineer either from sort of dumping HLO from the compiler or looking at sort of profiling output, I guess, on the GPU. But this sort of feels a bit like a reverse engineering task. I think that's not ideal. We need some tools to diagnose and to give information just about what kind of job it did on the partitioning, right? And sort of avoid having that clustered with all the sort of other information that is in profiling tools. That I think is really something for like that we should support tomorrow, but that's not there today.
Are there ways to nudge the compiler into what you want?
Yeah, so this is what you can do with these constraints, right? So in principle, if you would constrain every op, right? So sort of the sort of hypothetical extreme case, then it would do exactly what you would want it to do, right? Because then it becomes unambiguous because you've sort of put the compiler in a corner where basically everything is a constraint and it can decide nothing on its own. More realistically, though, you would look at the output and sort of decide where sort of are strategic points to put a constraint. Normally, what you do here is that there are some sort of fundamentally ambiguous places where the compiler might lose track of what is a sensible thing to do. Right, so think about reshapes, for example, right? Like in this case, sort of like all the values get shuffled around, and it's very hard to know, like, okay, where do the parallelization axes go after a reshape or a getter or something like that, right?
I've had this question for a while. Well, I don't know, maybe I haven't seen an API for this, but can like in compiled languages, you can tell them like, hey, compile quick or do your best. But in JAX I haven't seen like different modes of compilation. You know if this exists?
For accelerators, I think there isn't. Like there isn't a sort of big O mode. For CPUs, I think you can. There's like a flag somewhere where you can sort of tweak the LLVM optimization level that's used. But that's basically passed to LLVM, right? But yeah,
interesting. I don't know if maybe I should just put it as an issue in the JAX repo, because when you're debugging, you don't want XLA to take like a long time. But I guess if you're gonna run something that takes days, then I mean, even if it takes an hour compiling, then you wouldn't mind if it finishes quicker.
Yeah, I mean, this could be an interesting feature request to XLA to add sort of a fast mode for the accelerator compilers, right? That's what you're saying, I guess. Okay. So where was I? So what I just wanted to show as an example is sort of how quickly this gets ugly. Even if you would want to just manually write sort of the partitioning code in like right now in PMap or VMap or Xmap. And if you wanted to do sort of like a distributed map mode, right? So imagine you're sort of like doing model parallelism. So I call the axis model here. And it's basically like partitioning over the feature dimension. And so there's a whole bunch of things you need to do to actually do the communication, right? Like you have to figure out, okay, which piece of the pie do I have, and sort of communicate that to the other devices, like gather the outputs. Whereas with pjit, this is sort of like a very simple thing where you can say like, okay, I have some inputs, which is basically like there's a batch axis, there's like a data axis, and like a feature axis, which I call data and model for data and model parallelism. And then when you use none, you just indicate that it's not partitioned, that axis is not partitioned. And then it will essentially produce this code for you, right? Like it will produce the same code as the distributed matmul here. But it's sort of very explicit, and there's no way to make a mistake. And if you do this in a much bigger program, of course, then this really saves you a lot of code. Well, that's not the next shot. One thing, also coming back to something like deep speed, is that so what XLA do is what we call SPMD sharding. So it takes each operation and it creates a program that acts on a subslice of its inputs, and it generates just a piece of the outputs. And each program will execute all operations. Now in pipelining, that's a bit different because actually what you do is typically all the inputs and all the outputs are actually produced by the program still, but you get subprograms that they actually only compute a part of the compute graph, right? So you're splitting, you're distributing not the data over devices, but you're actually also distributing the operations. And so it turns out that in very big scale, like for example GPT-3, that actually means you need less communication. And you can sort of communicate asynchronously, right? Like that's where the pipelining comes from, where you can sort of start on a batch and then your previous batch is sent to the next device, and you get this sort of like this delayed programming where with the micro batches. And there's also some cool ideas about how you could generalize this. So for example, there's the pathways. So this is from the Google AI blog. Where pathways is like a sort of networking library where you can make this pipelining not just static, but you can actually make it dynamic, right? So you would have the data decide on which subprogram it needs to go next, and you get this sort of dynamic routing, which creates sparsity, and which allows you to sort of have a very big network that still operates relatively quickly. And that is also massively distributed across many devices. Here again, you could ask the same questions as with the mapping style parallelization, like, do you create these stages explicitly, or do you sort of have a magic optimization pass that just decides, okay, given a program and given some certain number of devices, find the optimal number of, or find the optimal sort of state boundaries, right? Like you could imagine that this sort of has an explicit and an implicit API that you could build around it. Today we don't have that, right? So, but we definitely want to support that eventually. So this, I think, is one of the interesting side effects of pipelining. I think is that it sort of enables the really big players to build something really large scale, but also some of that technology can also be given back sort of to the community and sort of improve the democratization of AI a bit, because you can take these really large models, at least when they're trained or when they're pre-trained, and now you sort of run each stage on the same device, and you're just streaming in and out the parameters, making clever use of the RAM that your host machine has, or even like an SSD or HDD, like sort of backup storage. And now you can fine tune these really big models, even though they have way more parameters than you have GPU memory. You want to say something?
I have a comment about this. I think this is not, like, I think this could go to the day-to-day of certain people, especially the Kaggle community. Maybe Sanjan has more experience there, but I believe Kaggle gives like competitors. I don't know if it depends on the competition, but you do have a TPU environment. Correct me if I'm wrong. And I have the sensation that nobody uses it. And maybe it's because it's kind of hard, like to leverage it. Maybe it would take like some investment into how to figure what is the optimal way. But then like something like Pidgit sounds like, well, I mean, just use it and it will figure out a way to speed it up, which I think, I don't know how much the Kaggle community has explored using the TPUs, but it's something that could, I mean, help help people in this kind of settings.
Yeah, I think I'm not sure if the sort of the one VM setup has been supported, like the TPU VMs, whether that's also supported on Kaggle. I'm not sure about.
I think it's the same. I don't. It also applies to Collab, right? In Collab, you get 8. I guess it's the smallest unit.
Yeah,
you
but
get 8 devices.
In Collab, you do still have the old 2 VM setup, right? So you're sending off the compute to the device, which does somewhat limit what you can do, right? So you'll have to sort of put everything on the device.
On the device, you mean because you have to send the data?
Yeah.
I see. But even then, wouldn't like something like this help, like to speed up the training?
Yeah, so I guess, I mean, also the issue with Kaggle, I think, is that for a long time we've seen that people have been very eager to try out machine learning sort of, or deep learning approaches, right? And then these would sort of be the very sort of avant-garde of machine learning approaches, like something like GPT-3. It really depends on the type of data that you have, right? Like if you have like tabular data and you don't have a lot of it, it's still pretty hard to basically beat decision trees, right?
Oh yeah. I meant more like the image competitions. Like, I mean, if you're if you can only train on a batch of 2, I guess it would really help if you could train on a batch of 16, something like that. I don't know if the IO would screw with that, but I just have the sensation that it is like, I've never seen a notebook that turns on in a TPU setting, and maybe it's because it's not so easy without something like Pidgit, right? You have to do everything, and I mean, you might be losing time.
Yeah, I'm not sure. I would be interested to know if people have already tried the approach of fine-tuning a large pre-trained model and try to win a Kaggle competition with that. I would be curious. I'm not sure if that's even like supposed. Are you allowed to do that? Or I guess everything goes right in Kaggle.
There are some restrictions, but like that is part of a lot of winning models. It's also like a part of ensembles.
Yeah. Yeah. Okay. I think I should look at Kaggle again. It's been a bit of time since I've last looked. I should see what's the winning approach now.
Ensembles. Can you for ensembles put a model per device?
Yeah, you can do that. You can VMap and use that to train an ensemble.
Oh, that would be
VMap or Xmap. That's pretty nice, I think.
Would be interesting.
Yeah,
I don't know, giving Kaggle some ideas how to use the TPUs, because I never see them used. I imagine maybe if they have something like JAX, it might be simpler, because on TensorFlow, I don't know how easy it is to use TPUs. And actually, there's a question about like differences between TensorFlow and JAX.
What's the question?
The exact question is,
they're asking the comparison between how does JAX compare against other deep learning frameworks, broadly speaking.
Broadly speaking, well, I guess of course the really the number one biggest difference is that it uses a functional API, right? Like there's no like in every framework right now that I've seen, there's like a variable abstraction in part of the fundamental sort of graph. There are some technical differences, I think. Of course, the NumPy sort of like making the NumPy the central API for compute, I think is another one. The functional transformations, I think, are also somewhat unique. The way they work also with this sort of tracing mechanism that I think is also interesting. Also, I think like what I find curious also is that the way gradients are calculated, I think, is also quite unique in JAX. That there's sort of this principle where you can do both forward and backward gradients. I think this used to exist in frameworks like Theano, but then sort of disappeared and reappeared again in JAX. And also sort of making XLA really the sort of universal compiler and working directly with that and making the IR work with that is sort of unique, I think. This is pretty nice if you want to create new transformations, right? Because I think what happened in the old frameworks is that people wrote specialized functions to make things faster, right? So for example, if you had like an activation function that was used a lot, people would make a custom function for that, right? Because otherwise it would just like, you wouldn't have a GPU kernel for it. And then for every little sort of like elementary function that it would use, it would move the stuff in and out of the GPU memory. But because JAX was built directly on XLA and XLA relies on fusion, right? So if you write your custom activation function, it will bundle all the ops together and generate the GPU kernel for you. We never had the temptation, like JAX never had the temptation to sort of overload the intermediate language with custom operations for the sake of performance, right? That I think has made the implementation a lot cleaner, which makes it easy to develop new things and also write custom. Like I haven't seen sort of other frameworks have this community where people actually create, like try to create new transformations on top of the IR that the intermediate representation that, for example, TensorFlow or PyTorch provides, which I think makes sense because for legacy reasons, they have like perhaps maybe even like 100 or more ops, and JAX has very few.
I have I mean, there's been a curiosity as to why TensorFlow like still doesn't rely like fully on XLA as JAX does. It's kind of curious because XLA lives in TensorFlow.
Yeah, that's true. But then sort of the TensorFlow compute model is older than XLA, right? And so there are some things that the TensorFlow model can do that XLA can't, right? Like the most obvious one being dynamic shapes, right? So the upside of having sort of this repertoire of ops that have a custom kernel is that you don't need to compile afterwards, right? And so now you can have sort of dynamic shapes, right? And XLA today cannot yet do that, right? So it cannot generate programs. This is also the main limitation of JAX, right? Like once you compile something, which is kind of what you need to get good performance out of it, you need to have static shapes, right? Now I think in deep learning actually that rarely actually becomes an issue.
I think that is more of an issue for serving, in my experience.
Yeah.
And I don't know if you can comment on this, but I noticed that JAX to TensorFlow now has like this like dynamic shapes, but JAX doesn't. So it's curious, like how was that achieved?
Yeah, so JAX to TF, if you use the TensorFlow ops, it will support dynamic shapes. Now, supporting dynamic shapes in JAX in principle wouldn't be such a big deal, right? But getting it compiled into XLA is what is the main issue, right? So in principle, you could add dynamic shapes relatively easily into the JAX intermediate language. And sort of the JAX to TF transformation is already kind of doing that.
Yeah, well, I mean, I implemented something with that recently, and like that wasn't always there. I remember I had to specify the batch dimensions directly, and then it was kind of awkward because like if you wanted to produce like something in TensorFlow serving or something like that, you had to specify like, oh, I only support like 1, 4, 16.
Yeah.
And yeah, like you really want to just specify whatever, and you can do that now. But I guess, as you're saying, that is not part of XLA. That is just part of how you convert it to TensorFlow.
Yeah. Yeah. So maybe in the future that will change, right? But
there is a related question. Maybe I don't know if you're gonna cover it, but like if like JAX is suitable for like industry applications.
Yeah, so I think you've already mentioned, right, like a big downside, which is the dynamic shapes. JAX has been very research focused, and I think it's kind of nice to think that way. For Flax, it's sort of the same. JAX to TF has been our sort of main way to avoid having to think too much about serving. And sort of tap into all the infrastructure that was already built for serving into TensorFlow. Yeah, so I think for sort of at least the short-term future that will probably be how it works.
Yeah, I'd actually say if you manage to compile it to like a saved model, then JAX is good for the industry. If you know like the TensorFlow ecosystem. I don't know, like I used it a lot, so for me that's kind of enough. I don't know if people have other needs, then you can hesitate.
Yeah, so this is one of the questions that we also wonder about, right? Like, can JAX to TF actually just solve pretty much 99% of the serving needs, or is there something we're sort of missing? I think so far it has worked, right? Like so far, like for example, the sort of dynamic shapes you mentioned, like we figured out that was sort of something that was needed in the transformation to TF, and that was added. So And there are a few more things like that, right? Like sort of like figuring out the sort of complexities of translating from one IR into the other. But I think nothing really fundamental is broken there. Okay. I'll pick up the slides again a bit. I guess how much time do we have still, actually, or is there a?
If it's okay for you to go ahead, I know we scheduled an hour, but if you'd like to wrap up, we can wrap up as well.
Okay, no, I'll go a bit more, but just for me to know this.
Thank you.
So I guess actually here some of the more perhaps ambiguous, but perhaps also more exciting stuff is because here really everyone can contribute, and you don't need the 1,000 GPUs in this quadrant of the helicopter view. The other part of research is just to actually do research and try new ideas, right? And I think there's also been a lot of exciting things happening there, and also in the JAX community. What's harder here is that this is not an engineering problem, right? Like this is just trying out new ideas, and sort of there's infinite possibility here. So it's not an optimization problem or just figuring out a nice API. You actually don't know what to expect. And we want to avoid getting stuck, right? Like we're trying to not have the ML stack dictate what ideas you can actually try out. And so I think the only way to do that is to make APIs that are unopinionated and sort of general, and that maybe where people will say like, look, all I need is pipelining, you know, but maybe we should say no. We actually want people to sort of fully have the possibility to try out all kinds of networking, or you know, like generalization also means that we can potentially catch an opportunity where someone figures out a new way to do things that turns out to be really great, right? So we should not just try to implement the status quo, but actually leave room for people to try out new things. I think JAX transformations are a really cool example from that, right? Like the basic transformation, the basic things, right, are just taking gradients, compiling, maybe parallelization, right? But we want to try new things, right? Like we don't just want to do data parallelism, we want to do model parallelism or splitting up an ocean into segments, and we maybe even want to combine multiple of these things, right? So why should there only be one gradient? Maybe we want information about the Hessian, maybe we want natural gradients, maybe we want third order gradients, maybe we want per example gradients, right? Which turns out to be great for differential privacy, right? This JAX can also do, right? Even though it's perhaps not something that is sort of a regular thing today, but it's useful and it has mathematical interest. And so having this general framework for doing transformations, I think is one of the things that makes JAX very powerful. And of course, there's also the pretty simple IR. So if someone actually figures a new transformation altogether, it's also pretty easy to add that, right? And it's pretty, like most programs will also run relatively fast because the XLA compiler can sort of take these very minimal building blocks, right? Like linear operations, exponents, logarithms, sums, whatever, and it can sort of fuse it together into a fast program because it can generate the GPU programs for you. And so I think this very much lowers the entry barrier to adding new things to the ML stack. And so there are some next generation of transformations already in the work, right? So perhaps something to work around the static shapes, right? To sort of have the ability to automatically add masking. So you can feed a dynamically shaped input into a statically shaped program. There's now experimental work on taking a program and sparsifying it, right? So allowing it to operate on sparse inputs. There are sort of what I would call advanced gradient things like being able to differentiate through solvers and sort of differentiating implicit functions. Having faster, sort of higher order gradients, right? Where you can really calculate the full Hessian quickly in a sort of semi-optimal way. there's been work done on the sort of experimental JAX to TF transformation, which we were just talking about. And I think, I hope actually that there will be more sort of very interesting transformations. I'm thinking maybe other export options, like maybe someone can write like an ONNX output, or perhaps something to facilitate sort of production, like speeding up a productionized model, right? Like transformations to allow you to use quantization or sparsity options in modern hardware. Right? And so one of the important things Flax has to do is it has to like support all these magic like JAX transformations, right? But it's already sort of in the name. Like these transformations you can do, and you can do them correctly because you're transforming a function, right? Well, which in this case has to be really like a pure function, right? Because if something has side effects, then for example, it's really hard to write a correct mapping transformation. But of course, with Linen, we actually add state to JAX, and now it becomes less obvious how you, for example, do like VMAP or any other transformation. And so what Flax transformations do is they take the existing JAX transformations and they augment them with state and randomness, right? So they allow you to put PRNG sequences and variables and lift those into a transformation. And sort of how this internally works is it will take the submodules and it will change them. It will turn them into a pure function, then feed it into the JAX transformation, and then sort of feed the output back into the state machine. And so what you can then do, for example, is you can say like, hey, I have like a dot product attention layer, and now I want to VMAP it, and I want to say like, oh, actually, I'm also going to VMAP the parameters, right? So I might actually add an extra dimension to the parameters. So now I have like a multi-head attention layer, right? And you can decide how that affects the PRNG sequence as well, right? So of course I want different parameters, right? I don't want the parameters to be initialized in the same way. So you should actually split the RNG when you're mapping it. But perhaps I want dropout to be the same, right? Maybe I want to use the same dropout mask anywhere for some reason, and yeah, you can control all of that. And so I think here again you can sort of think about interesting ways in which you could not just apply these transformations sort of in your training loop, but you can now put them directly inside your model, right? And so here again, there's sort of interesting new ideas that come up. One sort of interesting idea is to use combinations of scan and the remat transformation, which is sort of gradient checkpointing, which allows you to have like a constant compile time. Christian was just complaining about compile time, I think. So what you then do is you sort of roll up your model, right? In the depth of your model into a loop, basically. And so now, however, no matter how deep you make your residual network, it always has just this one layer that it just keeps on repeating with different parameters, right? And so now the compile time is constant. And if you combine that with remat as well, you can also get this like square complexity memory consumption, right? Because you can do optimal checkpointing. Actually, you could even add multiple layers of this, and you could get even lower memory consumption. So this is one way in which you can sort of like avoid like having exploding sort of memory and compile time if you try to train very deep models. But there are, I think, even more creative ideas that you could do, right? So you could try to sort of incorporate gradients into the network, where maybe you're running a solver inside the network, or you're doing something like meta learning or custom gradients, or whatever other thing. I think this is a pretty underexplored area where people could try new things. And generally, I think sort of the clues that we should use is that probably many ideas won't be exactly new ideas, but sort of using old solutions to new on new problems, right? There's already a lot of science, and I'm really excited seeing a lot of libraries appear that use JAX to do science and speed it up with the ML stack, right? So to run it on GPUs and TPUs. Like there's JAXMD, for example, which does molecular dynamics on JAX, so allowing you to do it massively parallel. That type of stuff I think is really cool, and also gives us new challenges, right? So for example, we've been pretty restrictive in how D types work in Flax. We didn't think about it that much. So we default to float 32, and then we support like half precision types for performance. But now there's people saying, hey, I'm doing like I'm fitting like a wave function with a Flax neural net, and for that I need complex numbers, right? Why you should support complex numbers as well? Why should I always use float 32? That's really cool, you know. Like beforehand we were like complex numbers. Nobody needs that. But now, like, we've got other scientists that actually know they're smarter than ML scientists, I guess, and so they know how complex numbers work. I mean, I already get nines with float 32, so I wouldn't dare to try. But they know how to preserve like holomorphic functions, and they know how to make it work, and then we can support complex numbers and make them happy.
Wow.
I think on D-type support, but generally on numerical precision, I think a lot of things is changing, right? NVIDIA has made their lives very hard by designing a very multi-purpose GPU that has a lot of new features that gives like ML infrastructure builders headaches, because they support like a gazillion D-types and even like integers, right? So they now have like a matmul unit that can do like int8, int4, truncated float 32. It can have like this 2 out of 4 local sparsity pattern where you provide a bit mask and it will sort of like for every 4 parameters, there will be 2 masked out to 0. But how do you support this, right? And of course, it won't stay this way, right? Like there will be other accelerators that have slightly different sort of sparsity and quantization features. And how do you support this, right? Because now we're just basically using IEEE standards, but this is way more complex than that, and this is going to explode. And how to support that in JAX and Flax, I think is still very much an open issue, right? And how do you support research, right? Like, of course, you can take a trained model and then quantize it to int8 and then run it. But perhaps you actually want to make use of the fact that this is much cheaper to run during training. But how do you do that, right? Like, how do you take gradients when you're doing matmuls with int8, right? Like now you need to, again, compose transformations, right? Because you might have to first take the gradient and then do the quantization, right? And then run it in a training. And this is going to be interesting, right? Because this is going to cause problems. But I think JAX is very much, it can do it yet. Nobody can do it yet. But I think we're sort of in a unique starting position to support these kind of things. I think that will be very cool. And what I hope is that eventually we'll reach the stage where we can use the building blocks, we can try really cool new creative ideas, and the ML stack won't limit us. And then if it actually works, it's very easy to scale up that great idea. Well, after we get funding for GPUs, of course, but then we can combine great ideas and using all of science together with massive scale and good engineering to create the perfect models, right? So what that means for us as sort of infrastructure developers is that we should make sure that the basic building blocks are truly easy to use and sort of safe, and that the APIs I think are best functional and definitely should be declarative, and of course we should create minimal friction for ML practitioners. And I hope that we can scale these ideas and also sort of make it still approachable for people to use, right? So we should be able, if a model works very well and we have a checkpoint, we should be able to get that on everyone's machine, to fine tune and win Kaggle challenges, right? Like, why are we not winning Kaggle challenges?
It's a good question for Sanjan.
I will end it with that.
That's like a mic drop point, honestly.
I do have something that it's kind of again like a devil's advocate, because well I went through it. I noticed, and I don't know if there's this kind of in the roadmap of maybe JAX or Flax, or is it kind of we'll solve it later. But if you know Keras or you know PyTorch, suddenly JAX is much harder for for certain things. You have to kind of figure out how to do like certain details, obviously because of the functional like I mean functional programming is not that great in Python. It's kind of so not like very focused on functional programming, and then also because I feel you have to be more explicit, which I guess is a trade-off, right? Is kind of a trade-off, but like are you thinking about this? Is this kind of a thing of how to onboard new people into into Jax and Flax, especially given like the huge like Hugging Face event? I guess that a lot of people suddenly started creating Flax models, but um, I think that might be like not a research issue, but more of a how to like a UX issue or something like that.
So actually we spend like, especially in the Flax thing, we spend a lot of time thinking about this. We don't simply assume that everyone's like, oh yeah, the functional paradigm is great. We don't think that everyone thinks like me, right? And like, I mean, I'm from a background, like I love like languages like Haskell and Rust, but I know I'm a bit of an oddball. I still prefer recursion over for loops, but I know that not everyone agrees. But yeah, I think it is also our responsibility that if we believe these things are great, we should also explain them, right, cleanly. And we do spend a lot of time on that, right? Just documenting what's already out there, and sort of explaining these functional paradigms. But we're definitely aware that this takes some extra effort to explain.
Okay, yeah. Yeah, no, this is kind of a comment I'm interested in. But I don't know, maybe you have some pointers we could share to the viewers. Like not here, there are people in different levels if you see the questions that I've been asking. So I don't know if we could link to something that you think it's kind of the easiest way to understand Flax. Obviously, you just go to the docs, right? But
the easiest way to
start like getting onboarded with Flax, or maybe I don't know if you have kind of a course as part of the Hugging Face. I'm not sure that was a thing.
Yeah, so on the read the docs, there's a guided tour, which has a few. So it starts here, right? So yes, there's not a link to. So it starts with some explanation of JAX, also related to the things you need to know for Flax in particular, and then you end up with some notebooks, like running through the notebooks for the Flax basics, so explaining linen and an annotated MNIST example. So I would start there. Maybe read some of the design notes and the additional material, and then I would run through one of the sort of more serious examples like the ImageNet or the WMT example. Just try to figure that out, like run it, and that should get you started, I think.
Thank you. Jonathan, just to be respectful of your time, is it okay to squeeze in another question from the audience?
Oh yeah, sure.
So Yuvraj is asking, can you share more resources on pipelining for democratization of AI? This is from your slides, and he's not sure if there are some already in the official guide, but he's just curious about it.
Oh yeah, so by the way, I added specifically tomorrow, right, to indicate that, and tomorrow is always like one day further ahead, right? We always say like, so if you want to learn about pipelining today, sadly, I'll have to refer you to DeepSpeed, right? But, or I had the particular example of pathways, right? Like which also works today, which is not exactly the same thing, right? Like I think DeepSpeed is particularly the sort of the resource that many people use today. So I would look at that for now.
Okay, thank you. I'll quickly wrap up and remind the audience that you can find Jonathan on Twitter. His handle is his first name concatenated with the second. Check out the Flax repository, check out the JAX repositories. You'll find him quite active there. You can also find Christian on Twitter at cgarcia_e88. Make sure you find him there. Any other resources or platforms you'd want to mention, Jonathan?
Yeah, I mean, if you want to chat about Flax, then check out our repository, Google/Flax, and we're pretty active there and try to sort of engage with open source and develop further from there. So yeah, just join the discussions or the issues page. Yeah, let's build something great.
Okay. Awesome. Jonathan, thanks again for your time, and Christian, thank you so much for helping make this happen. I'll wrap up here, but it was really a privilege to learn from one of the core contributors and one of the core developers. So thanks for your time.
Yeah, thanks for having me.
Yeah, thanks, Jonathan. It was really nice.